I am Professor Caudill, and I wanted to start by fixing a small mistake we made last time. So we were finding this displacement, and I don't know why I put in pi, but this should be -20 displacement. So my bad. Um, Let me write something. Radians equals pi over 180. So we had 180 degrees converted to radians. So maybe this makes a little more sense. Converts degrees to radians. Alright, so picking up where we left off. Polar coordinates. So it's kind of what we've been doing already. So Cartesian is hard when we're describing the rotation. In coordinate location, P in a plane is given by 2 polar coordinates. So we have our origin, we have our point P, so this is R, so R is all of this, R is that length, that's your radial coordinate. Second is a polar coordinate, phi, that is that the radial vector makes some chosen direction. Okay. Polar coordinates angles are measured in radians. A radial vector is attached to the origin. Points away from. So we have our radial coordinates, if I'm understanding it right. The second unit vector t is a vector orthogonal okay. This might not be the correct illustration, but we'll see if we can correct it later. Positive t direction indicates how the angle phi changes in the counterclockwise. So maybe it's arrows this way. All right, so our drawing seems to be correct in some ways. So angle phi for polar. Okay, so x equals cosine. So this is just building off of what we've already learned, basically using the trig formulas. So it's saying this point is moved here, and P is R, the length of the X, and phi. So instead of saying XY, it's saying it's X in the angle. And this is, so phi's radians, I'm sorry, R, phi is radians, right? I just read it, so bear with me. Angle phi. All right. Angles are in radians. Okay. So T, vector T, so vector T defines the positive rotation. So vector T doesn't make sense totally to me yet, but let's see if we can get there. So let's try this example. A treasure hunter finds one silver coin 20 meters away. So R is 20 in the direction of 20 degrees northeast. So 20 times pi over 180, because we're converting it to radians. All right, so this is our polar coordinates, and they probably want to know the rectangle coordinates. I don't know why they just didn't say Cartesian. All right, so I didn't read the other part. So yeah, yeah, this just makes sense when the book does this. Phi S and finds 20 degrees northeast. All right, so R, the gold coin, 10 meters. Phi, the gold coin is, so going west, so that's 90 plus 20. So 1118 pi. Book seems to be getting something different. Phi s is pi over 9. Okay, we got that. So the book is getting 8, 9 pi. I wonder where we went wrong. So 20 degrees north of west. So I'm thinking 90 plus 20. Not right. Not sure that is right. Isn't 20 degrees north of east? Why we're not. Useless. How did they get 8 over 9? 8 over 9 is 80 over 90, which is 160 over 180. So they're saying 20 degrees north of west is 160. So he's saying 20 degrees north of west. Okay. So it's saying 180 is west. 180 degrees is west. And they're saying north of west. So it's 180 minus 20. Okay. And then, so it's 160 pi 80 equals 8,9 pi. Okay, so we figured out how they're getting it. Again, so that's an example where ChatGPT was completely useless. It did not know the context of what we're talking about. Now we can move on. Substitute coordinates to obtain rectangular for gold coin. Coordinates are okay. So with the polar coordinates, we want to know, or doesn't matter? It doesn't really matter, right? So the x s is 20 cosine pi over 9. So we're converting polar coordinates to rectangle. So what is this doing? Essentially, we have this vector, and we know the hypotenuse, and we know this angle theta or phi or r, whatever you want to label it. So we're breaking the hypotenuse down into its component vectors. So this would be xs, this would be ys. So this will give us a number. Let's see if it matches the book. So where we had 20 degrees times 20 times 20, 18 for the x ace, 18.9 for the x for the silver coin x. Okay, that works out. And sine 6.8. Okay, 6.8. So we have verified the xy coordinates of our polar thing is okay, and then we would just do the same thing for the gold coin. I don't know why they flipped these. I mean, if you're introducing it in one order, silver coin first, why don't you do that? But that's kind of nitpicky, I guess. So this is introducing k hat for the z-axis. So you might be wondering why is it not x hat instead of I hat? It's because the x line, the x one-dimensional plane extends for however long of a set you're dealing with. So I hat just is one unit in that direction. All right, so XYZ IJK. In three-dimensional space. Okay, so we need to remember all of this. I know this is going to be kind of a long-term thing, so let's just review. So polar coordinates, we have a kind of a r x component on the x. This is r, and we measure r based off of some angle phi. And that gives us our r vector. So when you know these, you can get the actual components. So I guess it's not correct to say this is r because r in this case is not equal to 18.9. It's not equals 20. So I guess we shouldn't say that. Maybe it's better just to say we know a hypotenuse, we know an angle. How do you find the component vectors? All right, so let's clear this. Vector A has 3 vector components. Okay, so we have vector A is vector A is an element of R3 space. So, and consists of an AX, AY, AZ. So A is the magnitude of the X times the direction vector plus the Y plus the Z. Two, 1, 3. 2, 1, 3. Okay, so you know the origin. So origin saying its beginning and its end. So A, the magnitude, the AX equals A end minus A beginning. So if I drive 20 meters and then I drive 30 meters and I want this to be my magnitude, then it's going to be 50 minus the 30, because that's the beginning of this. So the end is 50 minus 30 equals 20. So AX equals 20 in this case. So the magnitude of A is AX Y Z squared. Ah. All right, so if we're taking in dimensions, we're taking square root of the sum of the squares. So I wrote this because if we're going in 4 or 5 dimensions, um, so what's going on in this picture? We have our y vector that's described by the magnitude, or how much. So if this is y, if this goes at 10, and it's a magnitude of 10, and it's described, vectors have a direction, it's in the j direction, so it's being multiplied by, so our unit vectors, so j hat is 0, 1, 0, x, y, z. I hat is 0, is 1, 0, 0, and then k hat is 0, 0, 1. So these just signify what direction it's in. And then this red vector is the resultant. All right, so during a takeoff, this drone, its position with respect to a control tower all right, so we have a control tower. Control tower. During a takeoff, its position is, so, okay. The initial position is let's just say 100, sorry, let's say 300 I 200 J and 100 K. So that's its initial position. At the second position, or the next position, so initial, next position, it is 1200 I, 2100 J, and 250 K. What is this displacement vector? So it's going in this direction, then it's going in this direction. I should say it's going in this direction, and then it's going in this direction. So we want to know the displacement, which is a vector sum of these. So displacement will be P0, so these are vectors, plus P1 so D is now the displacement is going to be the square root of 1500 squared plus 350. So this is where we borrow from our earlier chapters. So we're going to say this is 1.5 times 10 to the 4. I'm sorry, 3. No, 3 plus 5, so it's 10 to the 5. So 1, 2, 3. So 3 plus 5 plus 2.3 times 10 to the 5 plus 3.5 times 10 to the 4. So, and this is all to the square root. So I'm gonna say this is 10.5, is 10 to the 5th, this is 10 to the 5th, and this is 10 to the 5th. Because 3 is greater than square root of 10, so we're gonna bump it up an order of magnitude. So we are going to have 3 times 10 to the 5th, because 1, 2, 3 to the 1/2, and 1/2 is the same as saying 3, so D is approximately 6 times 10 to the 5th meters displacement. So let's see if that's accurate. Okay, so 2.1, so they're getting 2.1, so they want it in kilometers. So we're going to say 6 times 10 to the 2 kilometers. Seems to be way off. So I think we should have subtracted them instead of added them. So that's probably where we went wrong. No biggie, we can easily fix this. So we're going to subtract P1, magnitudes of P1 minus P0. So So I guess I can't say this until I get the magnitudes of each. So I'm guessing. So the displacement magnitude is 9. $150. Okay, so now we can do our tricks. So the displacement of the whole is square the sums. So what's going on here? These are the magnitudes of the components. Now we're finding the magnitude of this. Um, so we have 9 times 10 to the 2, 10 to the 4. I don't know if we could do that because wouldn't we have to square the 9 as well? I think we would have to. So all right, so let's say this is 10 to the 3, so it's 10 to the 5th. So this is 10 to the 3, so that's 10 to the 6. And then this is 10 to the 4th. Okay. So I don't know if there's an easy way to do this. I guess I can invert it. So these together is 10. Eleven times 10 to the 5th. And 10 to the 4th is 1 times Is that the same? 10 to the 4th is equal to negative 10 times 10 to the 5th. So our final answer should be just 10 to the 5th. So this is going to be way off anyways. I mean, it'll be 10 to the 2 kilometers. And that's way off what we're getting. So let's restart. Um, all right, so I think we did a good attempt. I'm gonna move on. The average velocity vector of the drone and displacement 2.7. All right, so what is the magnitude of the drone's velocity vector? Okay. So first we have to so we're finding u. So this is interesting. I mean, it's saying you're going 15 meters per second in the x direction, 31 meters per second in the y. So it wants to know what's the magnitude of the velocity. So what's this mean if we were going to express it as one vector? So it would be 15 squared plus 37.7 squared plus 2.5 squared. So u is 35.2 meters per second. So in a way, this is saying the u vector is 35.2 in the so it's saying it's going this fast in this direction. So let me check the math. 37.1, 2.5, square root. Okay. So I'm trying to figure out what's the best sequence to do. So it seems they do the vector first. and then the displacement of this vector, they find that. So this is a vector with components. All right, so algebra vectors. So saying basically if you have a constant c times b plus u, then that's equal to cv plus cu. I is east, J is north, K is altitude. Okay. Military convoy advances its position through unknown territory with velocity. For I plus 3J plus 1/10 K. In what geographic direction would it be moving? All right, so it's getting pretty tough. So we're gonna take our time here. So it's moving. So this convoy is moving in this velocity vector. The convoy had to retreat, and it's a little bit above ground. So it's not exactly in the ground. It's more like a plane. So it's moving kind of like this in 3 dimensions. So if it had to retreat, which geographic direction would it be moving? So it's asking when, in what direction it would be moving when the retreat order is called, or is it asking if it's going anti-parallel? What is this direction? So um So if we're just going in a different direction, it's going in that way. So I think it wants to know. So I don't get why. How does geographic direction turn into degrees? Why wouldn't they want to ask like what's the polar coordinates or what? So anyways, so this question just doesn't make sense. I think it's just kind of poorly worded. Um, Generalization of a zero vector is called a null vector. Zero, bunch of zeros. So if A minus B, then A equals B is what this is saying. Alright, so resolving vectors into their scalar components in vector component form allows us to use vector algebra to find sums or differences analytically. To find the resultant of two vectors A and B, simply add them component by component. Okay, so if A is your AX magnitude times that, your Y magnitude times J direction, and the X magnitude, the Z magnitude times the K direction. And same with B. Then R equals A plus B is and I think you get the point. We're just gonna continue that. So in this way, are the sums. So R magnitude in the I direction where okay, so analog methods can be used to find components of the resultants in many vectors. Example, for summing n vectors, each vector k okay, so this is just a very compressed way to say it. Frx the resultant vector f magnitude so we have k vectors. So you're adding up all these vectors, which means you're adding up all the components, which means you are adding up each component individually. In general, for something very important in physics, with many physical quantities are vectors. Use this method in kinematics to find a resultant displacement vector and resultant vector. In mechanics, to find a resultant force vectors and resultants many derived vector quantities. Electromagnetics, resultant electric magnetic field vectors. Okay. Oops. All right, 2 minutes. I don't know if we can get far with this, but 3 displacement vectors lie on a plane. So we have their magnitudes and their respective angles. So we have 10 at alpha equals 35 degrees. We have 7 at beta equals 110 degrees. So negative 110 degrees is and y gamma is 30. So 8 the physical units of the magnitudes are centimeters. Resolve the vectors to their scalar components to find the vector sum. So we want to know what is that. So we want to find the scalar. So we want to find the x, y, this. So if we recall, that is, this is A, then AX is 10 cosine AY is 10 sine. So then R is going to be AX I. So we're gonna have it. The final answer is going to be something like this. We'll finish up next time. Plus, you get the point. So we'll plug these in to where they need to go. And that should give us our R vector and components of the others. So thank you guys for watching. I'll see you next time.